Welcome to the deep dive. Okay, so today we're plunging into something really fundamental. It's the very fabric of existence, the stuff that literally makes up everything around you, matter.
Hmm.
We've looked at a range of sources to really distill, what matter is, what it's actually made of, and how its sort of hidden behaviors shape our everyday world.
Yeah, it's all around us.
Exactly. So our mission here is to cut through the complexity, give you a shortcut to being well-informed, and maybe reveal some surprising things about this unseen world that makes up our own.
And what's really fascinating, I think, is that understanding matter isn't just, for scientists in labs. It's not just textbook stuff.
Right.
It's really about gaining a new way, a new lens to see every object, every breath you take, every sensation you experience. This deep dive should really uncover this unseen ballet of particles. They're constantly dancing around us, inside us even.
A ballet, I like that.
Yeah. And it could offer, well, quite a profound shift in how you perceive your world,
Okay, so let's start with the big one. What is matter?
fundamentally.
Yeah, at its core. Well, the basic definition is anything that has mass, takes up space or volume, and can be perceived, by our senses, directly or indirectly.
Right, like this table or the water in your glass.
Exactly. Your coffee cup, the air you're breathing right now, the ground beneath your feet, even something like air. It seems like nothing, right?
Right. Invisible.
We can't see it, can't easily hold it, but it fits the definition. You feel it when the wind blows, right?
Definitely.
And you know it has substance. I mean, that's why you can't inflate a balloon inside a completely sealed bottle.
Ah, good example.
Yeah, the air that's already in there leaves no room. It occupies the space.
Precisely. And when we talk about substance, we're really talking about mass. It's just a measure of how much stuff an object contains.
Stuff. Okay.
And takes up space that refers to volume, simply the amount of room something occupies. We kind of get these ideas intuitively, don't we?
Yeah, I think so.
Like if you drop some marbles into a glass of water,
Right.
well, the water level goes up.
Because the marbles take up space.
Exactly. They displace the water.
Yeah.
And the glass also gets heavier, right?
Yeah.
Which shows the marbles have mass.
Makes sense.
So these aren't just abstract concepts. Mass and volume, they're tangible properties we interact with constantly. Like pouring water into a full glass, it overflows because there's no more space.
Right. No more volume available.
Or weighing two identical tumblers, one empty, one full of water. The one with water is obviously heavier. Water has mass.
Simple demonstrations, but they really nail the concepts. Okay, so matter takes up room, has substance. And speaking of substance, there's something people often mix up.
Ah, yes. Mass and weight.
Exactly. Mass versus weight. It's worth clarifying this. Your mass, as you said, is the quantity of matter, the stuff. And that never changes no matter where you are.
Correct. Constant.
But your weight, that's different. It's the force of gravity pulling on your mass. So your mass would be exactly the same on the moon as it is here on Earth.
Same amount of you.
Right. But your weight, it would be much less on the moon, about 1/6, I think.
That's right, about 1/6. Because the moon's gravitational pull is much weaker.
So it's a subtle difference, maybe, but really crucial for understanding, how gravity shapes our physical experience.
It really is. It reminds us that our feeling of heaviness is actually about an interaction, a force acting on our mass.
Okay, now we've kind of established what matter is, but what's it made of? Let's zoom way, way in.
To the microscopic level.
Beyond anything you can see, yeah. All matter, everything, is made of unbelievably tiny particles. We call them atoms.
The fundamental building blocks.
Yeah. Imagine tearing a sheet of paper. You rip it again, smaller and smaller pieces. But even the tiniest speck you can manage. It's still recognizably paper, right? It has the properties of paper.
Yes, it retains its nature.
That's because, fundamentally, paper is made of these tiny particles, atoms, or combinations of atoms that carry all its essential properties.
And this idea took a long time to develop. Historically, people had different ideas. The ancient Greeks, for instance, thought everything was maybe combinations of earth, water, air, fire.
The classical elements.
Exactly. Some traditions included sky or ether. But then thinkers started proposing something else. An Indian philosopher named Canada, centuries ago, and later, much more formally, the English scientist John Dalton. They proposed that all matter was actually composed of these tiny indivisible units.
Atoms.
Atoms, yes. An atom is essentially the smallest possible piece of an element like gold or oxygen that still has the properties of that element.
Okay.
But here's a key thing. Atoms usually don't like to be alone. They rarely exist independently in nature.
They combine.
They combine. They bond together to form molecules. So a molecule is the smallest unit of a substance, could be an element like oxygen, or a compound like water that can exist independently and still shows all the properties of that substance.
Ah, okay. So atoms are the basic building blocks, but molecules are often the smallest stable independent units we find.
That's a great way to put it. For instance, you rarely find a single hydrogen atom floating around.
Right.
Instead, two hydrogen atoms bond tightly together to form a hydrogen molecule. We write it as H2,
H2.
or a nitrogen molecule, N-2 nitrogen atoms. Then you have molecules made of different kinds of atoms, like a water molecule, H-.
Two hydrogens, one oxygen. Classic.
Precisely. Or carbon dioxide, GeO, which is one carbon atom bonded to two oxygen atoms.
Got it. So molecules can be simple, just two identical atoms, or more complex.
Absolutely. And molecules are definitely bigger than individual atoms, but both are just staggeringly small. You can't see them with your naked eye, obviously, or even with a standard optical microscope. You need incredibly powerful tools like electron microscopes to even get a hint of them.
Wow. So these invisible particles, atoms, and molecules, they're the foundation, and their behavior that dictates everything we see and touch.
And that's exactly it. It's like the secret life of matter happening constantly at this particle level.
Okay, let's get into that secret life then. What are the key characteristics of these particles?
Right. There are essentially three main things to understand about how these particles behave, and these explain a lot about the properties of matter. First, particles of matter have space between them.
Space between particles, even in a solid.
Even in a solid, yes, though it's very small. We call this interparticular or intermolecular space. It's not just empty void. Think of it as dynamic gaps between the particles.
Okay, how do we know this?
Well, think about dissolving sugar in water. You take a glass of water, maybe mark the level, you add a spoonful of sugar and stir it.
The sugar disappears.
It dissolves, right? But here's the interesting part. The water level doesn't really rise, or not by much, certainly not by the volume of the sugar you added.
Huh. Why not?
Because the sugar particles, which are molecules, are small enough to actually fit into the intermolecular spaces between the water molecules. They slot right in.
Ah. So the water molecules weren't packed perfectly tightly to begin with. There were gaps.
Exactly. There were gaps, the intermolecular spaces.
Mm-hmm.
Now, if you dropped a spoon in, the level would rise because the spoon is huge compared to those gaps. It can't dissolve or fit in between.
Okay, that makes sense. So characteristic 1, spaces between particles. What's next?
Characteristic 2. Particles of matter attract each other. There's a force pulling them together.
Like tiny magnets.
Sort of, yeah. It's called the intermolecular force of attraction. This force determines how strongly the particles are bound together.
And this varies.
Oh, definitely. Think about trying to break a solid wooden block. It's hard, right?
Very hard.
That's because the intermolecular forces holding the wood particles together are very strong. Now try snapping a piece of chalk.
Much easier. Brittle.
Much easier.
Yeah.
The forces in chalk are weaker, so it breaks more readily. Or think about water droplets. When water falls, it tends to form spherical drops.
Yeah, why is that?
It's that intermolecular attraction again. The water molecules pull on each other, trying to minimize the surface area, and a sphere is the shape that does that best. This force holds matter together. It dictates things like rigidity, how hard something is, even surface tension.
So spaces between particles and forces pulling particles together, it's kind of a balance.
It is often a balance, yes. And that balance is constantly influenced by the third characteristic. Particles of matter are always in random motion.
Always moving, even in my desk.
Even in your desk. The particles in a solid are vibrating intensely in place. They possess what's called kinetic energy. That's just the energy something has because it's moving.
Okay, constant random motion. How do we see evidence of that?
Easiest way is diffusion. Take a glass of still water. Carefully add a drop of blue ink without stirring.
Okay.
What happens over time?
Well, the blue color slowly spreads out until the whole glass is evenly blue.
Exactly. Why? Because both the water molecules and the ink molecules are in continuous random motion. They're bumping into each other, jostling around, and that movement spreads the ink particles throughout the water. It's like a microscopic, never-ending dance.
A microscopic mosh pit, you said earlier?
Yes, something like that. Another way is to sprinkle very fine sawdust on the surface of water and look closely, maybe with a magnifying glass. You'll see the tiny sawdust specks jiggling around randomly.
Why are they jiggling?
They're being constantly bombarded by the invisible, moving water molecules beneath them. It's called Brownian motion, actually.
Wow. And this motion, does it change?
Yes, crucially, it's directly related to temperature. heat things up. The particles gain kinetic energy. They move faster and more vigorously. Cool things down. They lose energy and slow down.
Okay, so let's put it all together. We have particles with space between them, forces attracting them, and they're always moving, and that motion depends on temperature. What does this mean for the big picture, for the matter we see around us?
It means everything. This constant interplay, the strength of the attraction versus the energy of motion, and the resulting spaces between particles. This is what fundamentally accounts for the three primary states of matter we experience every day: solid, liquid, and gas.
Ah, the three states, right.
Think about it. If the attraction between particles is very strong, they'll pull close together, reducing the space, and they won't have enough energy to move freely. That sounds like
It's solid.
exactly a solid. Think iron, stone, wood, ice. Solids have a definite shape and a definite volume.
They hold their form.
They do, because the particles are packed very tightly, often in a regular pattern or lattice. The intermolecular forces are dominant, very strong. The intermolecular space is tiny, almost negligible.
So they can't move around.
They can't move from place to place. They just vibrate intensely about their fixed positions. That's why solids are rigid and generally incompressible. You can't easily squash them.
Okay, examples like iron, stone, sand, wood, gold, diamonds. Sugar particles, too.
Yes, individual sugar crystals are solid. Solids are usually opaque, though some, like glass or diamond, are transparent. Metals often have that shiny quality, luster. And solids don't really diffuse or mix under normal conditions because the particles are locked in place.
Right, solid state. Tightly packed, strong forces, fixed shape and volume. What about liquids?
Okay, liquid. Think water, milk, oil, alcohol. The key difference here is that liquids have a definite volume, but no definite shape.
They take the shape of their container.
Precisely. Pour water from a cup into a bottle. The amount of water, the volume, stays the same, but its shape changes completely.
So what's happening with the particles?
They're still quite close together, but not as tightly packed as in a solid. The intermolecular forces are weaker, not strong enough to hold them in fixed positions. There are larger gaps, more intermolecular space.
Meaning they can move more.
Yes, they have enough kinetic energy to overcome the forces partially and slide past one another. And they can move around within the bulk of the liquid. That's why liquids can flow. We call them fluids.
Fluids. Okay. Examples. Water, milk, oil, petrol. Most pure ones are transparent.
Most are, yeah, though mercury is a notable exception. It's a liquid metal, so it's shiny, lustrous. Liquids can diffuse, mix together, but usually much more slowly than gases. Think of stirring cream into coffee.
Right, it takes a little mixing. And some liquids mix well, like alcohol and water.
Those are called miscible.
And others don't, like oil and water.
And miscible, exactly. The forces between their own molecules are stronger than the forces between the different types of molecules.
Got it. Okay, so definite volume, takes container shape, particles can slide around. That leaves gas.
Gas. Air, hydrogen, oxygen, steam. Gases are defined by having neither a definite shape nor a definite volume.
They just expand.
They expand to fill completely whatever container they're in. Think about the air in a football. It takes the shape of the ball. Or the fragrance of perfume. You open the bottle, and soon the scent spreads throughout the entire room.
Why do they do that?
Because the particles in a gas are very far apart compared to solids or liquids. The intermolecular forces between them are extremely weak, almost negligible. And the intermolecular spaces are huge.
So they're just zipping around freely.
Completely freely, yes. They move rapidly and randomly in all directions, colliding with each other and the walls of the container. They can flow easily, not just downwards like liquids, but in all directions.
And because they're so far apart, you can squeeze them together, compress them.
Exactly. Gases are highly compressible. You can force the particles much closer together. They also diffuse very, very quickly because the particles move so fast and have so much space to move into.
Like smelling cooking from another room almost instantly.
Perfect example. Gases are generally transparent, not lustrous. Some, like oxygen and carbon dioxide, can dissolve in water to some extent, while others, like nitrogen, are mostly insoluble.
Okay, there's a good demonstration for this too, isn't there? With bromine.
Ah, yes, the bromine vapor experiment. Bromine is one of the few elements that's a liquid at room temperature, but it evaporates easily into a reddish-brown gas.
So you have a jar filled with this colored gas.
Right, and you take another identical jar, just filled with colorless air, and place it upside down on top of the bromine jar, maybe separated by a thin lid initially.
Okay.
Then you carefully remove the lid between them. What do you see?
The reddish-brown bromine color starts spreading upwards into the top jar.
Exactly, and the color in the bottom jar gets lighter. Eventually, both jars have a uniform, pale, reddish-brown color.
So the bromine gas spread out to fill both jars.
It did. It occupied the larger available volume. And the air molecules from the top jar also moved down into the bottom jar, mixing with the bromine. You just can't see the air because it's colorless. It clearly shows gases have no fixed shape or volume. They just expand.
That's a great visual. Okay. Solid, liquid, gas defined by particle arrangement, forces, and motion. But things can change state, right? Ice melts, water boils.
Absolutely. And this is where it gets really dynamic.
Yeah.
Matter isn't stuck in one state. It can transition from one state to another and, crucially, back again without changing its fundamental chemical identity. Water is still H0, whether it's ice, liquid water, or steam.
Right.
This process is called the interconversion of states of matter.
Interconversion. And what drives these changes?
Primarily, it's driven by two main factors: changes in temperature or changes in pressure.
Okay, let's start with temperature, heating things up.
Right. So if you take a solid, like ice, and start increasing the temperature, you're adding energy.
Kinetic energy.
Exactly. The particles start vibrating more and more vigorously. Eventually, they vibrate so much they overcome the strong intermolecular forces holding them in their fixed positions.
They break free.
They break free and start sliding past each other. The solid turns into a liquid. This process is called melting, or sometimes fusion.
And the specific temperature where this happens is?
The melting point. For ice, that's 0 degrees Celsius or 32 Fahrenheit at standard pressure.
Okay, so solid to liquid is melting. What about liquid to gas?
Keep heating that liquid water. The molecules gain even more kinetic energy, move even faster. They bump around more violently, increasing the gaps between them, further weakening the attraction.
Until they escape completely.
Until they have enough energy to escape from the surface of the liquid and fly off into the air as a gas, or vapor. This is vaporization.
Is that the same as boiling?
Well, vaporization can happen slowly from the surface at almost any temperature that's evaporation, like a puddle drying up. Evaporation is faster when it's hotter, of course.
Ah, okay.
Boiling is a specific type of vaporization that happens rapidly throughout the entire liquid when it reaches a certain temperature. You see bubbles forming inside the liquid, not just evaporation from the surface.
And that temperature is the
boiling point.
Yeah.
For water, that's 100 degrees Celsius or 212 Fahrenheit at standard pressure.
Okay, so increasing temperature, solid melts to liquid, liquid boils, evaporates to gas. What about going the other way, cooling things down?
Exactly the reverse happens. Start with a gas, like steam, and begin decreasing the temperature. The particles lose kinetic energy.
They slow down.
They slow down.
Yeah.
As they move slower, the weak intermolecular forces start to have more effect. The particles get closer together, the gaps decrease, and they transition back into the liquid state. This is condensation, or liquefaction.
Like seeing your breath on a cold day or dew forming?
Perfect examples. That water vapor in the air cools down enough to turn back into tiny liquid water droplets. The temperature at which this starts happening is technically the condensation point, which is generally the same as the boiling point for a pure substance.
Okay, gas to liquid is condensation, and then liquid to solid.
Keep cooling that liquid water. The particles lose even more energy, slow down even further. Eventually, they slow down so much that the intermolecular forces become dominant again, locking the particles back into fixed positions in a rigid structure. The liquid turns into a solid, freezing, or solidification. And the temperature at which this occurs is the freezing point. For water, again, that's 0 Celsius or 32 Fahrenheit, same as the melting point.
So melting point and freezing point are the same temperature, just depends which direction you're going. Same for boiling and condensation points.
For a pure substance under constant pressure, yes. Think about wax in a candle. When you light it, the solid wax melts into liquid wax near the flame.
Right.
Some of that liquid wax travels up the wick and vaporizes to burn, but some might drip down the side.
And it cools down and becomes solid again.
Exactly. It solidifies. It's a nice little cycle of melting and freezing right there.
And what about the energy involved? You said heating adds energy.
Yes. When a substance melts, solid to liquid, or vaporizes liquid to gas, it has to absorb heat energy from its surroundings to give the particles enough energy to overcome the attractive forces. Conversely, when a gas condenses, gas to liquid, or a liquid freezes, liquid to solid, the particles are losing energy and settling into a more ordered state, so they release that same amount of heat energy back into the surroundings.
So energy is absorbed going up, solid, liquid, gas, and released going down, gas, liquid, solid.
Precisely. And because the chemical substance itself isn't changing, water is still water, the net energy change for a full cycle, say ice to steam and back to ice, is essentially zero, ignoring any energy lost elsewhere.
Fascinating. Okay, so temperature is a major driver of state changes. What about the other factor you mentioned, pressure?
Pressure mainly affects gases because their particles are so far apart to begin with. If you take a gas and increase the pressure on it, basically, squeeze it into a smaller volume.
You force the particles closer together?
You do. You force them closer, increasing the chances they'll interact, and the intermolecular forces will start to take hold. If you apply enough pressure, even without changing the temperature much, you can force a gas into its liquid form.
Ah, okay. Are there common examples of this?
Oh, absolutely. Things like liquid oxygen or liquid carbon dioxide, which are used in industry or medicine, are gases stored as liquids under very high pressure. A really common household example is liquefied petroleum gas, or LPG.
Like in a BBQ tank or camping stove?
Exactly. Inside that metal cylinder, the propane or butane gas is under such high pressure that it exists mostly as a liquid.
But when you use it, gas comes out.
Right. Because when you open the regulator valve, you release the pressure. As the pressure drops, the liquid immediately starts boiling and turns back into a gas, which then flows out to be burned.
So pressure can turn gas into liquid. Does it work the other way? Reducing pressure turns liquid to gas.
It can, yes.
Yeah.
Lowering the pressure lowers the boiling point of a liquid. That's why water boils at a lower temperature at high altitudes where the air pressure is lower.
Right, I've heard that. Okay, temperature and pressure. Any other ways states can change? Is there anything, like, weirder?
Well, there is one rather unique process called sublimation.
Sublimation? What's that?
Sublimation is when a substance changes directly from its solid state to its gaseous state, completely skipping the liquid phase.
Followed straight to gas. No melting.
No melting at all.
Yeah.
And the reverse process, gas directly to solid, is also often included under sublimation, or sometimes called deposition.
Wow. What kind of substances do that?
Some common examples are camphor, that distinctively smelling white solid sometimes used in chests.
Oh, yeah, I know that smell.
Naphthalene, the main ingredient in traditional mothballs. Iodine crystals do it. If you gently heat solid iodine, you see purple vapor form directly. Dry ice is perhaps the most famous example.
Dry ice, right. It doesn't melt into a puddle. It just seems to vanish into smoke.
Exactly. That smoke is actually cold carbon dioxide gas, plus often some condensed water vapor from the air. The solid KUO yours turns directly into gaseous KUO. Ammonium chloride is another chemical that sublimes easily.
Why do they skip the liquid phase?
Essentially, for these substances under normal atmospheric pressure, the combination of their particle attractions and the energy needed means it's easier, or requires less specific conditions, for the particles to gain enough energy to break completely free from the solid structure directly into a gas, rather than first becoming a loosely associated liquid.
That's really cool, a direct jump.
It is pretty neat. It shows just how varied the behavior of matter can be at that particle level.
Okay, wow, what an incredible deep dive this has been. We've gone from just, feeling the air or seeing water spill right down into the hidden world of atoms and molecules.
The unseen dance.
The unseen dance, exactly. We've unpacked that fundamental idea. Matter has mass, it occupies space. And it's all made of these tiny particles, atoms and molecules.
Which are never still.
Never still, always in random motion, with spaces between them and forces attracting them. And understanding those three things, space, attraction, motion, is the key, isn't it?
It really is. It explains why we have solids, liquids, and gases with their distinct properties.
Yeah, the tightly packed solids, the flowing liquids, the expansive gases, and critically, how they can change from one state to another, melting, freezing, boiling, condensing.
Even sublimating.
Just by changing the temperature or pressure, it connects the microscopic world to everything we experience.
It absolutely does.
Yeah.
Which I suppose brings us to a final thought, a question for you, the listener, to ponder.
Okay.
Knowing all this now, knowing that every single object around you, the chair you're sitting on, the device you're listening on, even the air you're breathing right now, it's all a ceaseless ballet of these unseen particles, constantly vibrating, attracting each other, moving around, potentially shifting states. How does that awareness, really thinking about it, change how you perceive your immediate surroundings? Is there something in your life that seems completely solid, static, unchanging? Can you now imagine it teeming with this secret, invisible dynamism, this constant microscopic motion, just waiting, perhaps, for the right conditions, a change in temperature, a change in pressure, to reveal a completely different nature hidden within?